Hi, thanks for joining me today. I'm going to be evaluating the limit as n goes to infinity of 2 to the n over n and proving that that equals infinity. Now I know what you're thinking, this is a pretty straightforward limit. I'm going to be doing this in an unnecessarily difficult way, just because it's a bit humorous, but also more importantly it will introduce you to some pretty cool maths. And this is inspired by a series or a collection of videos made by Michael Penn, and I think he called all of these Overkill, and he would prove really interesting results, or pretty well-known results, in these really roundabout ways where you prove it in a way that's completely unnecessary, but does introduce you to some pretty cool maths along the way. So I'm trying to replicate that here. And the way we're going to be working out this limit is by firstly evaluating this integral here, the integral from a to b of f of x to the n plus 1 over g of x to the n dx, and taking the limit as n goes to infinity, where f and g are kind of certain types of functions, so we'll look at that in a moment. And this is inspired by a Putnam problem from 2017. And then what we're going to do is to choose a suitable choice for f and for g. Anyway, let's dive into this one. Okay, so we're going to start by proving a lemma, and that is for functions f and g from the interval a, b to the positive real numbers, with f and g distinct functions, but their integrals the same. So we have two functions f and g defined from the interval a, b to the positive reals. They're distinct, but their integrals over that interval are the same. And we're also going to define in to just be this integral here, the integral from a to b of f of x to the n plus 1 divided by g of x to the n dx. This lemma claims that these in's form a sequence of strictly increasing positive numbers. So let's prove this lemma. How are we going to prove it? Well, let's firstly prove that this is true. And well, that's pretty obvious because if you just plug in n is 0 into here, you just get the integral from a to b of f of x dx. And since f of x is a positive function, its integral will be positive as well. So that's pretty straightforward. Next, I guess we'll prove this guy here, that I0 is less than I1. And the way we're going to do that is by considering I1 minus I0. And that just by definition is the integral from a to b of f squared over g. And I'm deliberately going to not write all the x's here just because I'm being a bit lazy, minus the integral from a to b of f. So when you plug in n is 0. Cool. Just using the linearity of integration, I can bring these into one integral. So it's the integral from a to b of f squared over g minus f. Okay, well, I can write this. In fact, what I'm going to do here, the trick is I'm going to add and subtract something. So the thing I'm going to add and subtract is, not from b, so from a to b, sorry. Let me write this again, f squared over g minus f. And then I'm going to add, add on g squared minus fg all over g. And then I'm going to subtract this again, so minus g squared minus fg all over g. And this is all still being integrated here. Maybe I should use some brackets here and here. Okay, cool. So I've added and subtracted the same thing. It seems a bit odd, but let's see why I've done that. If I put all of these guys here under the same denominator, what do I get? Well, I get the integral from a to b of f squared minus fg plus g squared minus another fg all over g, like so. And then what about this thing at the end? Well, I can cancel the g's with that g and that there, and I've just got minus the integral from a to b of g minus f, like so. Cool. Now the great thing about this is this guy here is just 0. And why is this just 0? Well, because of this fact up here, that the integrals are the same. So when I subtract them from each other, then integrate, that would also turn out to be 0 as well. So I can kind of ignore that term. And now what about all of this here? Well, the numerator factorizes quite nicely. So this is just the integral from a to b of f minus g squared all over g. And now, since f and g are distinct functions, f minus g squared is going to be strictly positive, or at least strictly positive on some for some value in this interval here. And if I divide it by g, it's still positive, and this is always a positive function. So this will be strictly positive. And so if I1 minus I0 is positive, we get that I0 is less than I1. I guess here I probably should mention that f and g are continuous. So maybe I'll add that in here. So f and g are continuous. So not super important, but for this last step, just to avoid any kind of trivialities where you make f and g different at just one point. So yeah, if we assume they're continuous, this is definitely true. Cool, so this is this inequality proved. Now we still need to prove all the remaining inequalities, but to do that we can use a very nice trick. Okay, so we're going to prove the remainder of these inequalities by using the Cauchy-Schwarz inequality, which I've written here. This just says that the integral from a to b of p of x squared dx multiplied by the integral from a to b of q of x squared dx is at least the integral from a to b of p of x times q of x dx, and then that whole integral squared. Now, how do we use this here? Well, what we're going to do is start by considering in times in plus 2. Now, just by definition, this is the integral from a to b. In is f to the n plus 1 over g to the n, and in plus 2 is the integral from a to b of f to the n plus 3 over g to the n plus 2. Now, we want to use this Cauchy-Schwarz inequality, so we're going to get this integral here to be this integral here to be this, and so we need to define p and q. So this guy here will be p squared, this guy here q squared, and so according to the Cauchy-Schwarz inequality, this is bigger than or equal to the integral from a to b of p, which would be the square root of f to the n plus 1 over g to the n. And again, we don't need to worry too much about this being well defined. Well, I mean, it is well defined because f and g are both positive. And then what about this guy? That's going to be the square root of f to the n plus 3 over g to the n plus 2. And then all of that squared there. Okay, but we can actually now just use basic properties of the surds and bring these two together. So we get the integral from a to b of the square root of, if I multiply the numerators together, I just get f to the 2n plus 4, and then on the bottom I've got g to the 2n plus 2, and then all of that squared. Okie dokie, but now because 2n plus 4 and 2n plus 2 are both even numbers, I can actually just square root this. And so this is the integral from a to b of just f to the 2n plus 2 over g to the 2n plus 1, all squared. But now that integral there is precisely in plus 1. So this is just in plus 1 squared. Amazing. So we get that in times in plus 2 must be at the least in plus 1 squared. And if we just rearrange this, we get in plus 2 over in plus 1 is at least in plus 1 over in plus 2. And kind of repeating this inequality inductively, sorry, that's supposed to just say in there. Whoops. We get that this thing here is bigger than in over in minus 1, and so on, all the way down to I1 over I0. But we've already proved that I1 is bigger than I0, and since they're both positive, I1 divided by I0 must therefore be strictly bigger than 1. And so in fact we get that each of these terms here is bigger than 1. So in particular, in over in minus 1 is bigger than 1, and so in is bigger than in minus 1, and we get that this sequence of inequalities is true, that this is an increasing sequence of numbers. Amazing. So that is our proof complete, but we can actually go one step further and say, in fact, using induction, in over in minus 1, this thing here must be at least, sorry, not in over in minus 1, in over I0 must be at least I1 over I0 to the power of n. And this is just easy to prove by induction. You just kind of repeat this inequality a bunch of times. And now this thing here we know is, well, this implies that in must be at least I0 times I1 over I0 to the n. This guy here is a positive constant, and this thing here, the thing inside the brackets, is bigger than 1. So in is bigger than a constant times something that's bigger than 1 to the power of n, and so this is going to go to infinity as n goes to infinity. And so this in fact proves that in not only is it an increasing sequence of numbers, it's an unbounded sequence of increasing numbers, and that's going to be crucial for us to evaluate our limit. So let's summarize what we've got so far. We've proved that if f and g are functions from a, b to infinity, or 0, infinity, and again we kind of assume they're continuous, with their integrals the same but they are distinct functions, then the limit as n goes to infinity of a from a to b of f to the n plus 1 divided by g to the n equals infinity. So now all we're going to do is choose values of a and b and functions f and g. So I'm going to choose a equals 0, b equals 2, and my functions f of x and g of x. F of x is simply going to be x, and g of x is just going to be the constant function 1. Okay, let's check this meets the conditions. Well, they're both continuous functions, and they both are from a, b to 0 to infinity, so from 0 to 0 infinity, that's both fine. And are their integrals the same? Well, we can just manually check this. The integral from a to b, or the integral from 0 to 2 of f of x, which is just x, that's going to be a half x squared from 2 to 0, which is a half times 2 squared, which is 2. And what about the integral from 0 to 2 of 1 dx? Well, that's just x between 2 and 0, which is just 2. And so they are the same, well, their integrals are the same, but they're definitely distinct functions. So now we can apply this result here. So the limit as n goes to infinity of the integral from 0 to 2 of f to the n plus 1, so that's going to be x to the n plus 1 over g to the n, which is just 1 to the n, dx is going to equal infinity. But well, what is this integral here? It's the integral from 0 to 2, or the limit as n goes to infinity, of the integral of x to the n plus 1 dx, and that's just 1 over n plus 2, x to the n plus 2 between 2 and 0, and that's just 2 to the n plus 2 over n plus 2. And so we prove that the limit as n goes to infinity of this equals infinity. And so just by doing a little index shift, the limit as n goes to infinity of 2 to the n over n also equals infinity. So a really nice way to make a simple problem much more difficult. But along the way, we've proved this pretty neat result here, that if you have two functions whose integrals are the same and they're continuous and positive, then the integral from a to b of one function on the top to a high power divided by the other function to one less than that power tends towards infinity as you make the power bigger and bigger. I hope you have enjoyed this video, and do let me know if you want to see more kind of proofs of simple things using some really I guess powerful tools, I guess. So let me know in the comments below. Apart from that, if you are new to the channel, please do consider subscribing and giving this video a thumbs up if you've enjoyed it. Thanks so much for watching. I'll catch you in the next one. Have a great day.